is she will switch on the videos, and that's a pre-recorded video about 15 minutes, and then you can ask the question.
Yeah, understood. I'm asking, she is already on the call?
Yes. She's with me only here at Roorkee.
Okay, just wanted to make sure.
We will now start formally the session 3A on analog mixed signal and RF, part 3. We are happy to have with us Dr. Shreya Sen as the session chair for the session 3A. There are 4 pre-recorded videos, and there are 4 speakers who have joined in this call. There will be attendees in the back end which none of us will be able to see. So that will be from our back end web developer side. They are not allowed to come into this meeting. All of us will have video as well as audio rights. And admin is at IIT Roorkee. So with this few words, let me start today's session by welcoming Dr. Sen, and it is a pleasure to read his bio. Dr. Shreya Sen is an associate professor in ECE at Purdue University and received his PhD degree in ECE, Georgia Tech. He has served 5 years in industry experience in Intel, Qualcomm, and Rambus. His current research interest spans mixed signal circuits, systems, and electromagnetics for IoT, biomedical, and security. Dr. Sen is an inventor of quasi-static human body communication, for which he is the recipient of the MIT Technology Review Top 10 Indian Inventor Worldwide Under 35. Dr. Sen's work has been covered by more than 250 news releases worldwide, invited appearances on TEDx Indianapolis, Indian National Television, CNBC, TV18 Young Turks program, NPR subsidiary Lakeshore Public Radio. Dr. Sen is a recipient of NSF Career Award 2020, AFSR Young Investigator Award 2016, NFS CISC CRRI Award 2017, Google Faculty Research Award 2017, Intel Outstanding Award 21, Intel Lab Quality Awards for Industry-Wide Impact on USB-C type, Intel PhD Fellowship 2010, IEEE Microwave Fellowship 2008, and 7 Best Paper Award, including IEEE CIC 2019 and IEEE Host. Dr. Sen's work was chosen as one of the top 10 papers in the hardware security over the past 6 years. He has authored or co-authored 3 book chapters, over 160 journal and conference publications, and has 15 patents granted or pending. He serves as Associate Editor of IEEE Design and Test, Executive Committee member of IEEE Central Indiana Section, and Technical Program Committee member of DAC, CIC, DATE, ISLPD, ICCAD, ITC, VLSI Design, and others. Dr. Sen is a senior member of IEEE. With this wonderful biography of Dr. Sen, let me welcome him, and I hand over the proceedings to Dr. Sen.
Thank you, Dr. Dasgupta, for the kind introduction. You could have cut it maybe a little bit short. Let me welcome everyone to this session on analog mixed signal and RF. Today, like Dr. Dasgupta mentioned, there are 4 talks. Our first talk would be on adaptive forward body bias voltage generator from ST Microelectronics. And our speaker is Vivek Tyagi from the same place. I hand it over to Vivek for the presentation.
Again, my name is Vivek Tyagi and I'll be presenting the paper which is titled Adaptive Forward Body Bias Voltage Generator. So I'll be discussing the introduction, existing solutions or the prior art, operating principle, the proposed body bias generator, the application in the NVM peripheral circuits, the simulation results, and at the end conclusions. So let's begin with the introduction. We all know that the performance parameter of any CMOS technology is strongly dependent upon the threshold voltage of a device that we have. So because the various parameters such as the transconductance, operating speed, FT, maximum drain current, all are directly or indirectly related to the threshold voltage. The threshold voltage exhibits significant dependence upon the process variation. So change in the value, because since the fabrication is a random process, so any change in the either in the substrate doping, the work function, it could result into the variation in the threshold voltage from its nominal value. The problem arises when the threshold voltage increases too much such that it would result in the degraded performance in terms of a more delay or I should say the reduction in the maximum drain current that could be allowed from a device. The maximum, there will be increase in the on resistance of a device, so such sort of thing will arise. So the solution that is present in the literature is the forward body biasing, which allows the possibility of reducing the threshold voltage to achieve the desired performance. Now let's discuss the existing solution. So there are so many solutions present in the FDSOI technologies where simply voltage doubler stage or charge pump circuit is used to generate 2 VDD, or a negative voltage generator that is used to generate the minus VDD for biasing the P-well or the N-well bias voltage. Advantage of using such a scheme is that in the FDSOI technology, the channel is isolated from the bulk, so there is no leakage current from the bulk itself. When we bias any positive voltage to the well of the NMOS, let's say the P well of the NMOS, there will be no leakage current flowing. But in the bulk based CMOS technology, if we apply any positive voltage at the P well for the, let's say for the NMOS case, we will have a forward bias of the junction and we will have a leakage current to start flowing through the junction itself. So that is a challenge in the well based technology. So for generating the bias voltage in the well-based technology, it is a complex task. For example, in this solution, a slew rate detector is being proposed, which detects the slew rate by charging of a capacitor through some digital logic, and then the pulse which is generated is then its frequency is then compared with the fixed known frequency, and then it is being used to generate the fixed body bias voltage, the modulating body bias voltage. So that's the problem statement, as I mentioned in the previous slide, that it is a challenge for the biasing of the bulk junction in the bulk based CMOS technology, because since the forward current through the bulk diode is significant, dependent upon the exponential function of the biasing voltage. So there could be a significant leakage current because of the exponential dependence, and the current through the junction, the bulk junction, would also be strong dependent upon the operating temperature. So suitable bias voltage needs to be generated for the correct and the optimal forward biasing of the N well or the P well. Otherwise, you would end up in the situation of a large leakage current consumption. Now let's move to the operating principle. As I mentioned earlier, so in the here it is shown the cross-sectional view of the NMOS and the PMOS. We have a junction diode that is formed between the P well and the source and the drain junction. So this is this diode, and similarly for the PMOS, this is between the N well and the drain and the source junction. So when we say the forward body biasing, then we are interested in forward biasing this diode such that this will result in the reduction of the threshold voltage of a device. So how we are going to generate it? So this is the simple idea that what we are want to achieve is that we would like to bias this diode that is present inside this inside the NMOS itself. So between the bulk and the source and bulk and the drain, we have these two diodes that is shown here, and we are biasing it with a fixed known current I bias. So I bias by 2 current will flow through one diode. So the voltage developed across one diode will be simply the Vt times natural log I bias by 2 times Is. In this equation, we have a design parameter of I bias. Vt is the thermal voltage, Kt by Q, and the Is is the saturation current for the diode, reverse saturation current for the diode. Similarly, this is for the PMOS counterpart. When the voltage drop across the diode will be VDD minus Vp, which is again equal to the same Vt times ln I bias by 2Is. So this we also call as a replica bias circuit, because at the end of a day we would like to bias the N well of the let's say the P well for the case of NMOS for our target application. So this simply diode will simply act as a replica branch, because at the end of a day this voltage that we have developed, this Vn consists of entire information of the temperature, as it is also tracking the temperature, and it exhibits all the properties that should be there in the ideal forward body bias voltage. Since this when we bias it to the any other well, then it also limits the leakage current that could flow through it, because we are generating it to a fixed known I bias current. So this really helps. As I mentioned earlier, that those two circuits are called replica bias, but we cannot directly bias these voltages to our target application, because there will be a leakage current flowing through these voltage. So these voltage that we have generated earlier, the references, they need to either provide the voltage, either they need to provide the current load, or they need to sink the current load. For example, in this scenario, the voltage that we will apply, so what I'm trying to say is that these two nodes will simply act as a need to act as a voltage source, because whenever they will be applied to either N well or the P well, they need to provide the current. So we cannot directly use this replica branch to bias the target application. So in order to do that, either we could upscale or downscale it using either using the divider circuit, or if there is no need of a divider, we could simply just buffer it. And the buffer is a voltage regulator. It should be a voltage regulator, so that it could track the node voltage Vp1 and Vn1 correctly, even when there is a large leakage current requirement, or leakage current need to be provided, or current need to be synced. And the target circuit could be any digital logic which we would like to enhance its speed, or either the periphery of the SRAM or the NVM circuit, or any analog circuit where we would like to improve the transconductance of a device. Let's move to the proposed forward body bias generator. So here it is shown in the figure. So we will have this replica bias circuit, and this is a unity gain buffer circuit. This is for the case of the NMOS. So in case of the NMOS, what we need to do is that this VBN node needs to provide the leakage current load. That is why we have used a PMOS in the loop, which is going to provide a large amount of a leakage current that could be flowing through the the P well of the NMOSs. Similarly, this is for the case of the PMOS. Here, this is the Vp volt with the from generated from the replica. Then we are buffering it, and here we are using the NMOS in the final stage. Since this node needs to sink the current, so the NMOS will be adaptive enough to draw the large amount of a leakage current that would be injected inside this VVP node. Now this slide is showing the schematic diagram So the architecture wise, both the voltage regulator are pretty much identical. Only difference is that in the first for the NMOS implementation, we have to use the PMOS as a final stage to provide the large current load, and here for the PMOS scenario, we would like to use the NMOS in order to sink the large current load that will be injected inside the VBB node. Now move to the application. So this is the typical peripheral circuit shown of a non-volatile memory array. So we will have some pre-decoding logic, which is nothing but some NAND or NOR logic, which we have to use in order to select some word line, and we will have some word line driver stage, which is nothing but some inverter or buffer stage which needs to drive the large capacitive and resistive load of the individual word line. So this is just the detailed schematic is taken from this reference. So it's simply a digital logic which could be further enhanced, or its operating speed could be improved by simply applying the forward body bias voltage to their N well and the P well respectively. Now let's move to the simulation results. So it is generated and designed in the 90 nanometer CMOS technology. The design is done using only the low voltage transistor for a supply of 1.2 volt and considering a temperature range from -40 to 175. The layout area was around 4200 micrometer square. The bias current is around 1 microampere for both NMOS as well as the PMOS in the replica branch circuit. And for the compensation of the regulator, 3 picofarad of a compensation cap and 25 kilo ohm of series resistor is used for generating a zero, and they are stable for up to 40 picofarad of cap load and the current load of 40 milliampere. Now this result shows the trend. So this green plot shows the replica bias output of a replica bias circuit VN, which is generated by injecting a current inside the diode which is present in the NMOS. So the junction that is formed between the P well and the N plus junction of the drain or source, and VBN is the output of this voltage regulator. Similarly, this is the VP node which is for the PMOS corresponding. So we could see that the regulator is able to track the variation, and in the x-axis it is the temperature, so it is also showing the trend of a temperature. So the diode forward, the voltage drop across the diode decreases as the temperature increases. Similarly, here it is showing the load regulation of the voltage regulator. So it is depicting that for up to current load of 40 milliampere, the voltage regulator is able to keep the output within the sufficient range. So there was no degradation at the output voltage level. So this plot is showing the reduction of the threshold voltage. So this blue plot shows the threshold voltage of the PMOS for the device dimension of 1 micro by 1 micro with FBB, and this pink plot shows the threshold voltage of a similar device but without FBB. So it is depicting that up to 38% reduction is observed at -40 and 21% at 175 degree. Similarly, this is for the NMOS. So up to 46% is reduced at -40 and 52% at 175. This is the plot showing the word line rise and fall delay of this row decoding architecture that I have shown earlier. So with the help of FBB, we could simply gain up to 17% just by biasing of the N well and the P well of the driver and the pre-decoding stage. There is no need to increase the sizes. The similar sizes would give directly improvement in terms of a 17%. And here is showing the VT reduction for the typical temperature of 25 degrees. So up to 48% could be reduced and 34% for the PMOS. Now coming to the conclusion. So adaptive on-chip FBB voltage generator is presented in this brief. Output magnitude of a FBB generator is dependent upon a fixed current. As I mentioned earlier, that in the equation of the forward body bias voltage, we have only single parameter, which is the bias current, which is going to define the magnitude of the forward body bias voltage. The leakage current also will get limited, because the I bias that we use to bias it will keep the leakage current up to only similar magnitude if the well area is also similar, if the junction area of the replica bias circuit and the target application is same. So if the well area increases, then the leakage also increases. But again, we could play with the bias current in order to reduce the leakage current as well. And the target application for it was in the row decoding path of the memory array, and it successfully it is demonstrated from the simulation result that it is advantageous to use it. Let's thank you for that.
Thank you, Vikas, for the presentation. Thank you, Vikas, for the presentation. So let's see if there are questions from the audience. If not, I have a question.
Yes, please.
I wonder there is a lot of echo.
We are trying to. So Siddharth, can you switch off your mic, please? Siddharth, Kala.
Yes.
Now, is it okay, Dr. Sen?
Yeah, let me try. Yeah, this looks okay. Perfect. Thank you for fixing it.
Thanks. Please go ahead.
So Vikas, can you hear us? Oh, sorry, Vivek.
Yes,
I apologize for mispronouncing.
Professor, I can hear.
Okay. So I have a couple of questions. So you presented the data that your DO can support up to, or the driver can support up to 40 milliamps of current. So do you have a sense of how much current would be needed for your block? And of course, that depends on the size of the block. So do you know what forward bias current are you looking for per micrometer of device size?
Well, Professor, this is just the proof of validation of our idea that the regulator that we are designing, it could support the large leakage current required if the target N-well or the P-well area is increased. As you know, we are showing the periphery of our memory array, and you know the periphery is simply in the entire in the pitch of the memory array itself. So the row decoding would be in just in front of the word lines, and the column decoding in just below the memory array. So depending upon the area size, we will depending upon the memory array density itself, we will scale up the periphery area, and that could be one area of concern where we could have a more leakage. So that's why we are showing that more leakage could be supported from the regulator itself.
Yeah, Suresh, just to add, because this said,
Yes.
you are calling me since the last 2 times, so I thought I should pitch in.
I apologize. I got confused with both the names.
No issue. Just to add, our idea is to limit the current from the source side where we are actually generating the driver. So over there we have this option. We can choose the area of the diode, the parasitic diode, as well as the biasing current for that diode. That can be even few, let's say tens of nanoampere as well. Okay, but let's say it should be significant large than the normal leakage current, so that circuit can work properly on silicon. And after that, wherever this voltage will be applied, FBB voltage will be applied, depending upon the multiplication factor of the area of the next diode where we are going to apply this voltage, the current will increase according to the multiplication factor of the input current. So
Right.
our idea is to limit the current from the input side itself so that the final current can be really decreased, the leakage current. And this driver is having the capability, because if you see the architecture, either the PMOS blast or NMOS blast will be coming in picture, and we can size it according to the current requirement where exactly this voltage will be applied. Did I
Got it.
answer your question?
Yeah, that's fine. Okay. I guess there are no further questions from the audience. So let's move on to the next presentation. Our second presentation is from IIT Bombay, titled 27S/32S DC balance line cloning scheme for PAM4 signaling. And it will be presented by M. Chandrasekhar. I welcome Chandrasekhar to the presentation.
Hello everyone, welcome to you all. Myself Meryala Chandrasekhar, and today I am going to present my work, that is a 27 symbol to 32 symbol DC balanced line coding scheme for PAM4 signaling. My co-authors are Sandeep Goyal and Professor Shalabh Gupta. We are from Department of Electrical Engineering, IIT Bombay. So now let's get into the actual details. This is the complete overview of our presentation. We'll be discussing all these topics. This is the abstract. I'll be discussing all these points in the summary in the last slide. Yeah. So why AC coupled transmission line is required? Because we need to isolate the transmitter and receiver in order to avoid the requirement of having same common mode. When we do this, we are creating one more problem, that is, generally the transmission lines are low pass in nature, but when we add this AC coupling capacitor, it will become band pass in nature. So the lower frequency signals are attenuated here. So when transmitter is trying to transmit continuous DC like data, this capacitor is blocking it. So at the receiver, we will be receiving wrong data. So this is called as baseline Wander phenomena. So on the left side, we are seeing it for binary data. On the right side, we are seeing it for PAM4 data. We need to avoid this baseline Wander. So in order to do that, we need to make this continuous DC-like data into a toggling data such that when we consider a chunk of word, the DC must be equal to 0. So in order to do that, we have many encoding techniques. So for PAM2, we have 8B to 10B. And for PAM4, we have 5S, 6S, 10S, 12S. Though we have it for PAM4, those implementations are very complex in nature, and also it uses very huge amount of memory. The proposed 27S to 32S encoding scheme is very simple in implementation, and also it has only overhead of 18.52%. So now let us discuss about the proposed encoding technique. So this is the background actually. So our work is based on the Knuth's method of balancing binary sequence. According to Knuth, a binary sequence of even length can be balanced by inverting bits up to certain position in a sequence, either from left side to right side or right side to left side. I'll be explaining this with an example. Let us consider this binary data word, which is of even length, that is n equal to 8. And I'm trying to invert the sequences only from the right side throughout this paper. I'm not considering the inversions from the left side to right side. So when I try to invert the first bit, it contains equal number of ones and zeros. This is a completely DC balance sequence. When I invert up to third position also, we are getting completely DC balance sequence. So for sure we will be getting DC balance sequence if it is an even length sequence. So and I am representing this position index as I, which gives the information regarding till which bit we are inverting. So this position index we will be using throughout this paper. So the Knuth's method is extended to PAM4 also. There we are inverting bits, but we will be inverting here PAM4 symbols. So PAM4 data symbols are 0, 1, 2, 3, and its binary equivalent is this, and its DC value is -3, -1, +1, +3. So this is the DC value I am considering for this paper. So it is extended to inversion of symbols. So what do you mean by inversion of symbols? Means when I consider 0, 1, 2, 3, its inversion is 3, 2, 1, 0. So when we have data 2, I'll be inverting it to 1. When we have data symbol 3, I'll be inverting it to 0. When I do this, I'll be getting the possible minimum DC content is -3, -1, +1, +3. So we cannot make it completely DC balanced, but we can keep the DC as minimum as possible. So we need to transmit the information regarding position index also. So for that also we will be adding one position sequence, which also adds the DC to this existing DC, and it will create more DC. So in order to nullify that DC also, we need to have one more redundant sequence to make it completely DC balanced. So let us consider D as a 27 length data sequence, PAM4 sequence, and D bar of I are inverted sequences in which I'm inverting the symbols up to certain position, that is ith position. So when I equal to 0, it is the actual direct data, and possible minimum DC content is -3, -1, +1, +3. So we need to send the information regarding the position index I, and also we need to add redundancy in order to make it completely DC balanced. So consider this example D, and we need to find out all the D bar of i's. So for when position index is 0, it is the actual data. So DC of this is +40. When we are inverting data from the right side, we will be getting the minimum possible DC. That minimum possible DC for this example is -1. So now let us consider D as the input data sequence and E is the final encoded sequence. So we need to transmit D bar, that is inverted sequence, which is of length 27, and we also need position sequence in order to transmit the information regarding that position also, which is creating the minimum DC in the D data sequence. And also we need to have redundant sequence such that it will make the encoded sequence completely DC balanced. Position sequence. So it is used to represent the position up to which we are inverting it in the actual data. So number of position sequences are 28 because we are having 28 position indexes. So for that position indexes, we need to transmit the data. So we need to have 28 position sequences. So the minimum length to accommodate is 3. So 4 power 3 is 64. So we will be getting 64 combinations, but we will be choosing only 28 out of them, in which we have zero crossing transitions, and also we need to have minimum DC content. So the minimum DC content in the D bar of I is -3, -1, +1, +3, and also we will be maintaining the minimum DC in this position sequence also. So the minimum possible DC is -3, -1, +1, +3 here. So these are the position sequences chosen for this position index. So D bar of I has -3, -1, +1, +3, and position sequence P of I also has minimum DC. And after combining these two, data inverted sequence and position sequence, we'll be getting the minimum DC. That is the worst case DC as +6 to -6. So in order to nullify this produced DC, we need to have one more redundant sequence whose DC value will be exactly opposite to that of this produced DC. Redundant sequence. So we are choosing these redundant sequences 00, 01, 02, 30, 31, 32, 33. So two symbols are enough for creating this DC, and I'm considering K as the summation of symbols here. 31 is 4 and 32 is 5. Yeah. So we need to remember this. Based on this only, we will be implementing our encoder. So after finding all this, I will be concatenating this in a scrambling manner. Means I'm not going to concatenate it in the sequence, in the same sequence. This I'm doing because in order to create more transitions in the signal and to avoid the continuous run length. So implementation part. So implementation we are doing only based on the symbol value only throughout this paper. So let us consider this D as a data sequence of length n, and it's an M level sequence, and it is said to be DC balanced, completely DC balanced sequence if it is satisfying this equation, that is summation of symbols equal to n into m-1/2. So I'm considering this as a balancing value alpha. So for our proposed encoded sequence, 32 is the final encoded data length. So n is 32, m is 4, n into m-1/2 is 48. So our balancing value is 48. So summation of all symbols in the encoded sequence must be equal to 48. Based on this equation, we are going to implement. So from the table, summation of R is lying between 0 to 6. These are unique values. So I am considering this. and let 48 minus of this d bar of I and p of I equal to L. So based on these two equations, so there may be more than one possibility such that d bar of I and p of I is satisfying this equation. So if there are more d bar of I and p of I, we need to choose that d bar of I and p of I which has least position index. This is the encoder flow. If input data sequence is D, then we need to find all the d bar of I and p of I which is satisfying 0 less than or equal to L less than or equal to 6 equation. And out of these, we need to select the one which has least position index. So now we need to find out the redundant sequence R of L from that table and concatenate all these to get the scrambling pattern. This is the final encoded data sequence. So D is there, we are finding d bar of i's and p of i's. We are summing them and we are subtracting it from 48 balancing value, and then we are selecting those only which is satisfying 0 less than or equal to L less than or equal to 6, and also which has least position index. So from this, we will be selecting R of L, d bar of I and p of I. So and I will be scrambling it. So this is the encoding pattern. So let us consider this as a data, and we are finding all the L's. So L's lying between 0 and 6 are these 0, 2 and 5. So we are getting 3 such sequences which is satisfying that equation, but we need to choose that one only which has least position index. So I am choosing 12. So we need to have d bar of 12, p of 12 from the table, and for this corresponding I, we got L as 0. We need to choose R of 0, that is 0, 0 from the table. So now we need to concatenate into this scrambling pattern and transmit. So this is the completely TC balanced sequence. Decoder flow, if the encoded data sequence E is given, then we need to discard that redundant sequence and we need to find out that position sequence, and we need to decode that position sequence to find out the position index, and we will be using that I, and we will be inverting the symbols from right side till that position only. Then we will be getting the original data sequence. So this is the decoder architecture. We will be discarding this redundant sequence, we will be finding position sequence, and then we will be inverting that sequence. So this is the example, same example. We are just discarding this redundant sequence 0, 0, and 1, 1, 1 is the position sequence. Position index will be 12. So d bar of 12 is this one. D of 12 bar bar is the actual data. These are the simulation results. We passed it through a AC coupled transmission line. This is without encoding and this is with encoding. Without encoding, the eye is completely closed, and with encoding, the eye is completely opened. So these are the measurement results. So we have generated the data using arbitrary waveform generator and passed it through a DC blocking amplifier, and we observed at the oscilloscope. So this is without encoding, the eye is completely closed, and this is with encoding, the eye is completely open. So we did this measurements at 8 giga samples per second. So this is the conclusion. The proposed encoding scheme is for PAM4, and it removes the baseline Vander phenomena, and it has only overhead of 18.52%. The maximum run length is reduced completely, and it is very easily implementable. The future scope is we can extend this PAM4 to higher levels of data, and optimization of encoder and decoders is also possible. These are the references. Thank you. Yeah.
Thank you, Chandra, for the very nice talk.
Thank you, Dr. Shreyas. Yeah.
So it looks like we do not have any questions from the audience yet. We'll see if that comes in. In the meantime, I have a couple of questions.
Sure.
So how did you choose the 27? You could have done 13, you could have done 15.
Yeah, generally the output 32, right? I wanted to make that output as an even number.
Mm-hmm.
So and also if it is 2 power 5. So that if in that manner I have chosen output as 32 and input became 27.
I see. And then the overhead that you're putting, the 5 bits. So is there, what I'm looking for is there an analysis of your overhead versus the benefit you are getting as a function of the length and the overhead?
As a function of, okay.
So the number, you can think of the number. So total, okay, you're saying 2 to the power 5. It could have been 2 to the power 4, it could have been 2 to the power 6, right?
Yes,
And let's say even once you choose 2 to the power 5, that is 32, the padded bits, right, which is 5, that can vary from, it could have been 3, 4, 5, 6. So how the whole system is changing, the maximum run length and your DC balancing benefit, the minimum analysis you are doing. So is there an analysis of how you achieved with this 27 plus 5 number? And could it have been anything around it?
That analysis is not there, Professor Shreyas. While we are doing this, we thought an idea of inverting these symbols. And when we do this, the minimum possible DC in that data is we can achieve any odd length data. We can achieve that minimum DC only. So based on that minimum DC, how much DC we can. So we also need to send the information regarding position sequences. So based on those addition of those DCs, what redundant sequences we can use. So if that DC produced DC can be higher also when we choose different length sequences, and based on that we will be choosing redundant sequence. So the required redundant sequence length may be 3 or 4 when we choose different length of sequences. So our idea is only we have chosen it for 27 symbols, and we made it to 32, and we can extend this to higher length sequences, or we can reduce this to lower length sequences. But this is the proposed idea. We have chosen it as an example, maybe. Yeah.
Got it. Thank you for that answer. And then the other question is for this 2732 coding, so to say, what is the maximum guaranteed run length?
That exactly we cannot calculate, Professor Shreyas. Maybe around 11 it could be, but we cannot calculate it because it is dependent on the data dependent run length.
Yeah, but you can do some worst case analysis to say that in the worst case it would be this much.
Yeah, in the worst case it could be 11 to 12 that analysis we did, but not exactly. We cannot say exactly what could be the run length. It is a data dependent.
Sounds good. Yeah, PAM4 is picking up, so this is very interesting timely work. Thank you.
Yeah. Thank you, Professor Shreyas.
So let's move on to our next presentation. This is from IIT Bombay, Professor Mariam's group, who we have worked with in the past. The title is Low Power Extended Range Multimodulus Divider Using TSPC Logic. The presenter would be Prasad Kulkarni. I invite Prasad and welcome him.
So first of all, I would like to thank all the VLSID committee members for giving me this opportunity to present our work, and also for organizing this event virtually. So I will quickly go through the motivation, then I'll talk about conventional architecture, talk about proposed architecture, then its performance comparison, post-layout simulation results, and at last conclusion. So from the motivation point of view, due to the high data rate and large bandwidth requirements, the 5G standard actually has incorporated a number of narrow bands, which covers the frequency range from 450 MHz to 6 GHz. And actually this demands the frequency synthesizer to operate at high frequency with a wideband VCOs and divider. So the fractional frequency synthesizer with a delta sigma modulator is the well-known choice. And the delta sigma modulator will generate a fractional values, okay, which requires the divider to change its division ratio instantaneously. So the multimodulus dividers MMD are normally or always incorporated with the DDSM with the delta sigma modulators. Okay. Now, from the implementation point of view, the MMD can be implemented with the CML logic, TSPC or ESPC logic. Okay, but due to ease of implementation operating at high frequency, the TSPC logic is preferred. is a popular choice or preferred. So if you look at the MMD architecture, you can see there are number of 2 by 3 blocks. So these are the division by 2 or division by 3 blocks called as a dual modulus prescalers. Okay, so depends upon the value of r 1 or 0, it will divide by 2 or divide by 3. Now these blocks are connected in a cascaded, and also the output from last stage is connected to the previous stages. So there is a feedback from the last to the first stages, and it applied in input, the input operating input operating frequency is applied at the input, and the division, after division we get the output at a last stage. Okay, so from the implementation and design point of view, there are two important parameters, that is operating frequency of these prescalers, and the second is the power consumption. So when they are operating in division by 2 or division by 3, each will have their different propagation delay, and this will limit our the maximum operating frequency, and also it will decide our overall performance of our MMD. Okay, the second point is the power consumption. So the number of transistors are switching, the frequency at which they are switching, and the capacitance at each node will also decide our switching power. Okay, these are two main points. And then third is the our range of the MMD. So in the conventional architecture, we take output from the last stage. So the range we can actually get from 2 raised to n to 2 raised to n plus 1 minus 1. So for 6 stages, for example, for 6 stages, we actually get from a range from 64 to 127. Okay, so the 64 is the lowest division, and we cannot go below the 64 because we are taking output from the last stage. Okay, so if you look at the implementation at transistor level, you can see this is the conventional way of implementation, where the two flip-flops and connected to the OR and logic. So if you see this node, output of the second flip-flop is connected to the AND gate and the first flip-flop. Okay, and this is the transistor level implementation of each. Okay, so at this node they are connected with the AND gate and also the input of the D flip-flop. So at this node the capacitance increases, and large loading, due to large loading capacitances, power consumption increases. The second thing is, there is the when we want division by 2 operation, we make r is equal to 1. So we actually get division by 2 operation. So we need only one flip-flop, and our output is connected to this input through a AND gate, and we don't want this part. But because of this connection, this circuit keeps switching, and it increases the power consumption during division by 2 mode. And the third thing is the during the division by 3 mode, this logic at this point to transfer to this point. Okay, and it is getting transferred through this the OR gate and AND gate. So the propagation delay through these logic will limit our operating frequency. Okay, so these are some of the drawbacks, and we try to eliminate in our proposed architecture. So in the proposed architecture, we have done two important modifications. One is the NOR gate we have embedded between the stages, and output is taken from the initial stages. So this actually extends our range of division operations. Okay, so instead of taking the output from the last stages, so whenever we want to work with the lower ranges, like suppose if we want division by 8, we can have only 3 stages. We don't want the next stages, we can just cut off them. Okay, so that is the embedding of this NOR gate helps in extending the range of operation. Okay, and the second thing, we have designed these prescalers, low power high speed prescalers, which will the prescaler 1 is used in first block, and prescaler 2 is used in all the other blocks. Okay, so if you compare the proposed prescalers and conventional prescaler, the 3 important changes we have done that improved our performance. Okay, so the output here you can see is applied to this flip-flop, and output is applied to this flip-flop through the AND gate. Okay, so the thing is the same logic is being applied to this. Okay, and the sum of these nodes are getting switched with the same logic. Okay, so there are some redundant branches in the circuit. Okay, so there is possibility of we can eliminate those redundant branches. So in this proposed circuit we eliminated this branch. So these are the branches we have eliminated, and instead we took output from this node and directly applied here. So this arrangement we have done. Also the second thing is we have added this MOSFET. Okay, so whenever R is equal to 0, this will get cut off. R is equal to 0, the whole circuit will get cut off, and we will work with the one flip-flop. So this helps in division by 2 mode. Okay, so in division by 2 mode we need only one flip-flop. We don't want this circuit to switch. So this arrangement allows us to do and saves the power. Okay. The third point is whenever we are working with the division by 3 mode, because of the propagation delay of OR and AND gate, okay, this will limit our maximum operating frequency. Okay, so the logic we have to actually we observe the logic at this point and this point, and we actually saw the how the things are actually working. So we came with this point that this from this mode we can actually directly use the signal, and we can give it to the pre-charge MOSFET. So this MOSFET will turn on when this node will go low. Okay, and this will charge instantaneously this output node. Okay, and this will actually helps in improving the speed of operation during division by 3 mode. Okay, so these are 3 important changes we did. So we compared with the other 2x3 Prescalers because the conventional architecture consumes maximum amount of power. Okay, and after that there have been many improvements, many papers have been published. Okay, so what we did, we simulate with the other architectures with the same design, that is same W by L ratios for the D flip-flops, all the D flip-flops with the same node capacitances. Okay, so we considered 3 micrometer and NMOS with the 2 micrometer. So what we observed that we got a 67%, 69% power saving in division by 2 or 3 mode compared to the conventional architecture. Also the 30% and 48% saving in the PDP performance, that is power delay product performance, in division by 2 or division by 3 mode. Okay, to get the idea about just average power consumption, you can see that the 74 microwatt per gigahertz with the Prescaler one, and 110 microwatt per gigahertz is the average power consumption we got for in division by 2, and 73 and 76 microwatt per gigahertz. Also PDP we observed that is a 30 or 32 femtojoules. Okay, and 24 at femtojoules at 6 giga, all are observed at 6 giga. Okay, and which we found very closer to our reference circuit, which is a TSPC division by 2 circuit. Okay, so after that we actually embedded these circuits and in the multi-modules divider, and the Prescaler one used for first block we actually implemented with the 6-stage MMD. Okay, and we varied the VDD. Okay, and with the different process corners we actually check the maximum input frequency. So what we observed in the TT corner, we got 10.1 gigahertz operating frequency, and 14.2 gigahertz in FF corner, and 6 gigahertz in SS corner. We set all the divisions to 127 such that all blocks will operate at division by 3 and they will consume maximum power. Also at that frequencies, maximum operating frequency, we calculated the power consumption. Okay, what we observed is we got a 3.5 milliwatt at 10.1 gigahertz with the supply of 1.2 volts. So at this point, when supply voltage was set to 1.2 volt, we got a maximum of 3.5 milliwatt power consumption at 10.1 gigahertz operating frequency. So then we set a particular parameters like a supply voltage we set to 0.9 and input we applied 6 giga with the process corner of 27 degree in a TT. And for different divisions, we actually observed the power consumption. So for maximum division, we got a 1.6 milliwatt, and for lower division, 8 division, we got a 0.9 milliwatt. So the way the interstages are operating, the frequency at which they are operating and the division at which operating, also the power consumption varies. Okay, so we checked it at 6 gigahertz because our intended frequency operation is 6 gigahertz, even though it can work above that. Okay, so this is general comparison with the other blocks like CML, TSPC and ESPC logic. Okay, so if you compare with the same technology, you can observe that the CML operates at a high frequency, but it consumes the same large amount of power, and lower division ratio is also small. Okay, and if you compare this TSPC with the same technology, it actually quite operates at a high frequency, but the divisions are discrete. Okay, in the comparison, we actually chose only 6 gigahertz. Okay, and supply of 0.9, and we have actually continuous divisions from 8 to 127. Okay, so one of the reviewer actually told us that it may not be a fair comparison because these are some major results, all are, and this is a post simulation, post layout results. Yeah, that is a fair point actually, but we can actually think of a degradation of 10 to 20% degradation. Okay, from the TT corner. Okay, so I'm expecting to work at 6 gigahertz, but may get degraded because of PCB and other wire bonding effects and other things. So there is always scope that actually here we have, that we can actually increase our supply voltage to operate at intended range. Yeah. So in the conclusion, I can say that this architecture is a programmable, which gives the division from 8 to 127. Also realized with the two low power 2 by 3 prescalers. Okay, the maximum of power consumption is 1.6 milliwatt and lower is 0.9 milliwatt, operating at 6 giga with the supply of 0.95. Okay, the one of the drawback is that due to the stack structure of the proposed design, the propagation delay in the division 2 mode slightly increases, and also this limits to operate at lower supply voltages. Okay, so that's all.
Thanks, Prasad, for your nice talk. Let's see if we have any questions from the audience. Maybe wait a couple of minutes. For people watching, we encourage you to submit your questions through the chat.
No questions yet.
Okay, thank you. If not, let me ask a couple of questions. So, first question is, you stacked and you mentioned that because of that there is a delay challenge, but also, anytime you change the circuit, there is some positive that comes out, and there are some drawbacks that you have to give up. Do you have an idea on what is the trade-off of this architecture compared to the cascaded traditional architecture?
Yeah, so can you hear me?
Yes, we can hear you.
Yeah, so what we actually observed that we actually tried to improve the performance of the circuit, but because of we had to do some arrangement like putting one in NMOS in the stack structure, like, so because of that it actually just increased the delay in when we were working on the division by 2 mode. So it's like there are some drawback, but at the same time our power consumption actually improved because of that, and this actually limited our input frequency range because of the stack structure, but the arrangement and some of the redundant branches we eliminated, so because of that our power improved. Yeah, so
Understood. And I was also looking at your reference. Some of the papers I'm familiar with. There was Stefano Pellerano. His work was from like 2004. Also, some of the other works are from 2010 and 11. There is a big push for 5G, as you mentioned in your motivation, and there are a lot of new designs that are coming out in the last 2-3 years. Have you looked into a more recent reference, like looking into the last 3 years, which I did not see in your presentation, and find comparable designs and compare and contrast with them?
Yeah, so some of the designs were actually where means they didn't have any new changes in the architecture. Only thing that they have changed the technology. So in the new references, you can see the architecture remains the same with the conventional MMD, but their technology and other things they change, and they give a comparison of overall like a frequency synthesizer, complete frequency synthesizer, instead of giving the particular divider. So most of the JSSC papers are working towards the frequency synthesizers, and they have same divider structures, but the improvement is in the overall synthesizer. So yeah.
Yeah, that's a very good point. That I guess initially it was not clear from your presentation, but I think the audience will find it very useful that the reason you are comparing with the previous work is because you don't see a divider paper published with those specific numbers, just a divider paper today.
Yeah. Yes.
Yeah, but so, if you find some numbers like that, that will be useful to add if you were extending this work and things like that.
Yes.
But your point is well taken. So I think we're close to 10:30, so we will move my time. So we'll move on to the next presentation. So our next presentation, the last paper in this session, is from NIT Goa, and it's titled "A 1-volt double balanced mixer for 2.4 to 2.5 gigahertz ISM band application." The presenting author is Sanmitra. I welcome her for the presentation.
A good day to everyone present here. I am Sanmitra Naik, and today I will be presenting on a 1-volt double balanced mixer for 2.4 to 2.5 GHz ISM band applications. The team includes me, Sanmitra Naik, an MTech student in VLSI. Mr. Siddharth Arke is a research scholar. Dr. Anirban Chatterjee is an assistant professor who specializes in antenna design and RF circuit design. Dr. Nitin Kumar is the head of the Department of Electronics and Communication Engineering. Dr. Vasanta MH is the registrar of the institute, and we are from the National Institute of Technology, Goa. And Dr. Ramnath Kini is associated with the Cement Corporation in Malaysia. So, the contents of today's presentation include the objective of this project, the conventional architecture, the proposed architecture, the simulation results, conclusions, and the references. So, today we have a lot of applications in the 2.4 gigahertz and 2.5 gigahertz, which include the Bluetooth, Zigbee, and Wi-Fi applications. In today's world, we have a lot of devices which are being deployed as a part of wireless sensor networks and as a part of Internet of Things. And Bluetooth, Zigbee, and Wi-Fi are key contributors to these. So in figure 1, we can see a Bluetooth transceiver, and in this Bluetooth transceiver, we are focusing on the design of the down converter, and in that down converter, we are specifically focusing on the design of the RF down conversion mixer. So in this project, our objective is to design a down conversion mixer which has a high conversion gain while consuming a very low power of less than 1 milliwatt and having a noise figure of less than 20 dB. So coming first to the conventional architecture, in the conventional architecture, we have 4 transistors and 2 capacitors. So when the RF signal comes as an input, the VRFP gets multiplied with the VLOP, and we get the intermediate component VIFP. So in the positive half cycle of the local oscillator, we get the VIFP as a multiplication of VRFP and a VLOP, and during the negative half cycle, that is when VLON is high, we get multiplication of VLON and VRFN. So with this, we get a differential output VIFP and VIFN. Now, the multiplication would lead to the frequency components as RF plus local oscillator frequency. That is the RF frequency plus the local oscillator frequency, which would be the up converted component. And RF frequency minus the local frequency, local oscillator frequency would be the down converted component. Since we are focusing on the down converted mixer, we are interested in only the down converted component. Now, in the conventional architecture, since it is a passive design, we see a gain of only 2 by pi. Since this gain is not enough, we wish to boost the gain as the output signal amplitude may be much lower than what is needed. So in our proposed circuit, we have two stages. One is the switching stage and one is the amplifying stage. So in the switching stage, the local oscillator signal is multiplied with the incoming RF signal and we get the multiplied components. Now, the designed circuit operates at a voltage of 1 volt and is designed in a 180 nanometer technology. Since we have reduced the voltage from the nominal voltage of 1.8 volts, the transit frequencies of the individual transistor are reduced. As a result, the higher frequency component already has a very low amplitude compared to the down converted signal. So the need for additional filtering or the design complexity of the following filter would be reduced. So first, let us consider when the local oscillator signal is high, the RF signal would get multiplied over here. And here we would see the component VRFP into VLOP and over here VRFN into VLOP. And this would act as a difference amplifier, and at the output we would have the IF signal. And since this is a differential in nature, the other components such as the local oscillator frequency itself and the RF frequency itself would get cancelled out, leaving only the intermediate frequency components. And in the local oscillator, when the local oscillator is high, S1 and S2 would operate, and when the local oscillator signal is low, the S3 and S4 switches would operate, and this would get interchanged and the mechanism would follow. So coming to figure 4a, here we have the biasing network. So in this we can see that we have one transistor MB and a current source IB would generate the voltage across MB. So MB is sized such that the DC bias voltage generated is VDD by 2. Next, we have figure 4b, which is the common mode feedback circuit. So the common mode feedback circuit generates the common mode voltage, which ensures that the mixer operates in a stable mode, and that any deviation due to mismatch or process corner variation would be reduced. Next, we have in figure 5 the oscillator, which is used to generate the local oscillator signals. So we see that we have designed an LC oscillator, and the cross coupled pair M3, M4 and M1, M2 ensure that the output is set to a DC of VDD by 2. And we have a buffer which consists of 4 inverters, in which the inverter is sized into 3 for all the stages. Next, in figure 6, we see the layout of almost 15 dB. In figure 7b, we see the conversion gain versus the local oscillator power, in which we can observe that initially the conversion gain increases, then it settles down, and then it decreases. So when the local oscillator power is low, the switching action is not performed properly, and it is not sufficient to drive the transistors. When the power is sufficient, we see that the gain is almost constant between 15 to 20 dB. And beyond a power of 20 dB, it starts to deteriorate as the circuit no longer behaves in linear region. Next, we consider the output power with respect to the RF input power, and beyond an RF input power of minus 7.78 dBm, the circuit goes into nonlinear mode of operation. And similarly, for the third order input referred intercept point, beyond a power of 1.58 dBm, the third order harmonic would start to dominate over the first order harmonic. Next, we come to the Monte Carlo analysis for test case 1. So in test case 1, we fix the intermediate frequency to 10 megahertz and the input power to 30, local oscillator power to 20 dBm. And we observe that for both the post layout and the pre layout, that the standard deviation between the mean gain is almost 0.20 dB. Next, for the second test case, the local oscillator power is fixed to 5 dBm, and we observe that also in this case also that for the post layout the deviation is 0.19 dB. Next, we come to the noise figure versus the intermediate frequency. So as we can see that the noise figure decreases with an increase in intermediate frequency. At lower frequencies, the thermal noise tends to dominate, and at 10 megahertz, the noise figure is almost 18 dB. In figure 10b, we have the spectra of the RF and IF signals for the two-tone test. So in the two-tone test, we have considered two input signals, 2.41 gigahertz and 2.5 gigahertz. So 2.41 gigahertz is our desired input signal, which will get down converted to 10 megahertz, and 2.5 gigahertz is an additional signal which would get down converted to 100 megahertz. So we can see that at 10 megahertz, the signal power is almost 4 dB, while that of the 100 megahertz component is minus 20 dB. And we can also see that because of the two input frequencies, we have a lot of harmonics due to intermodulation. Now, since our desired frequency is at 10 megahertz, we can put a low pass filter and suppress all the frequencies which are undesired. Next, we come to the variation of the conversion gain and noise figure with respect to temperature. We can see that the noise figure increases with an increase in temperature and the conversion gain decreases with an increase in temperature. So coming to the comparison table, we have designed a modified passive mixer in a 180 nanometer technology at a supply voltage of 1 volt. We are targeting a frequency range between 2.4 gigahertz to 2.5 gigahertz, and we are fixing the intermediate frequency to 10 megahertz. Our circuit provides a conversion gain of 16.15 dB, which is moderate as compared to the other circuits. The noise figure of the circuit is a bit high, but this is because the power consumed by the circuit is much lower than the ones existing in literature. The area occupied by the circuit is also much lower than the other circuits existing in literature. Our circuit has a 1 dB power point of minus 8.54 dBm and a third order intercept point of 1.58 dBm. And the figure of merit 1, which takes into consideration the conversion gain, the noise figure, and the power is 22.17 dB. And the figure of merit 2, which also takes into consideration area, is 55.01 dB. So to conclude, a double balanced down conversion mixer was designed, and the proposed design provides a conversion gain of 16.15 dB and consumes a power of 222 microvolts. It occupies a small area of only 0.052 mm square, and the design can be used for applications such as Bluetooth, Zigbee, and Wi-Fi. And these are some of the references that we have used. Thank you. Any questions?
Any questions from the audience? Please type in.
There is one from the audience. What is that question? So there's a question from the audience. What is the effect of wire band by Shiv Kumar Gopal from Global Foundries? We have sent it to your chat box, Shreyas.
Okay, I'm trying to find. It's somehow not showing up on my chat box. I did. Oh, I see it now. Thank you. Okay, so I'll reiterate the question. It is asking that you mentioned about wire bond issues. What are the effects by wire bond? Sanmitra, could you hear us?
Can you repeat the question?
Yeah, so Shiv Kumar Gopal from Global Foundries is asking about the effect of wire bond because he says that you mentioned that about wire bonding issues.
Wire bounding issues.
You know how you wire bond a die?
Okay. No, I have not mentioned anything about wire bond. Maybe it was with respect to the previous paper.
Okay, so I think we can move forward from there. I do have a few questions for you. So you are cascading an amplifier after the passive mixer.
Yeah.
What is the bandwidth of the amplifier that you are using?
The bandwidth is around 20 megahertz.
So that's more like an IF amplifier, right? You are not passing any of the RF components there.
No, correct. But like what happens is some of the RF components will pass through, but because of the nature of the amplifier, due to the reduced voltage, they will be suppressed automatically.
Right. So the amplifier doesn't have bandwidth. If you look at the amplifier's plot, it has low pass kind of a response, and at RF you have very high loss. So you are not passing the RF. So it's an IF amplifier. So if I look at its topology, it is basically a standard passive mixer followed by a IF amplifier. I do not so I was trying to understand why are you calling the passive IF amplifier part of your mixer?
Okay, that can be how you look at it. Yeah, again, so maybe we did not think of, maybe we never saw it from that point of view, to be honest.
Yeah, that's
it can happen. It can happen that like someone also asked me like, why is this not a switched transconductance mixer? Like it looks very similar. So yeah, it may be like
switch transconductance. You have to have a transconductance active circuit that is getting switched, right? For your active circuit is not getting switched. Your active circuit is a standard amplifier which is in the IF frequency, and your passive circuit is getting switched.
Correct.
So yeah, but what you're saying is so yeah, I would like to call it passive mixer IF amplifier. Of course, one can define in different ways. So I do have another question. Which is, you mentioned about the noise, and you did say that there was a thermal noise. It was reducing over frequency. You have any comment about flicker noise?
Yeah, so thermal 1 by F noise is your flicker noise. So yeah, I did say thermal noise, but yeah, the flicker noise component is also there in that. So thermal noise, I think I may have interchanged thermal noise with flicker noise. Yeah, the graph actually does display flicker noise. So yeah.
That's great. You just want okay, yeah, that's all the questions I had. I do not see any other questions from the audience. That brings us to the end of
further questions.
Great. That brings us to the end of this session. Sorry.
Yes, you can close the session, and then I can.
Yeah. Thank you everyone for participating, and have a great rest of your day.
Thank you, Dr. Shane, for your sparing your time and effort to come. I think it's late night there, or
yeah, it's about 11 p.m. It's not that late. to keep the
I
values.
understand. Okay.
Okay,
Bye.
thanks.
Bye. Bye,
Bye.
all of you.